What's going on, smart people? Did you think that Christmas was over? Well, it is, but Kelly and I spent Christmas in Virginia, so we had to impose a sort of conservation of mass for our suitcases. We couldn't be pulling back all of these presents and then have to pay extra for more suitcase weight. So we decided to hold off on getting certain presents until we got home. Needless to say, another one came in today that I'm really excited to talk about, so I wanted to make a video about it. As you all know by now, I am a level 12 tensor boy, and what better gift for such a boy than an introduction to general relativity, Sean Carroll's textbook. I didn't actually own any textbooks on general relativity. The closest thing that I own was my tensor calculus book for physics, as well as some lecture notes given to me from a professor before. So this is a really cool book to have. It'll be nice to have a formal reference book that actually goes through derivations. It's not actually a reference book. It is a textbook for a first course in general relativity. So let's go ahead and go through some of these chapters so that you know what it covers. In my opinion, something that makes a physics book a good physics book is when it is self-contained, meaning you don't have to go to other references to fill in the gaps that the book left. For example, in Griffith's E&M, if you did not have vector calculus, that's okay, because at the beginning, the first chapter is a vector calculus review, and you use that heavily throughout the book. That is completely necessary, and you can always reference that branch of math, and it's also a sense of self-awareness with the book to point out this is the math most directly associated with this branch of physics. And this kind of has the exact same thing, because the first 3 chapters of this book are a math review. I say math review, but really I should probably say math introduction, because it doesn't actually assume prior knowledge of this kind of stuff. Certain branches of physics, like maybe special relativity, classical mechanics, things like that, there is a little bit of assumed prior knowledge, but even in chapter 1, it's also a review of special relativity. So chapter 1, special relativity and flat space-time, it goes over what you would think it would, 4 vectors, tensors, things like that. Chapter 2 is manifolds. Chapter 3 is curvature. So this is really going into the differential geometry and tensor analysis that general relativity demands. Chapter 5 is an entire chapter on Schwarzschild black holes. Chapter 6 goes over different types of black holes, like rotating and charged, but it doesn't look like rotating and charged, which I think are called Kerr-Newman black holes. Chapter 7 is perturbation theory and gravitational radiation, so it goes over gravitational waves. Chapter 8, cosmology, that's where it actually gets into things like gravitational lensing, which is pretty cool, and the Friedmann equation, scale factors, redshifts. And then Chapter 9, which is pretty great, quantum field theory and curved space-time. No, that is not a chapter on string theory. It just goes over things like the Unruh effect and Hawking radiation. The reason I say that this is a textbook, not a reference book, is because, at least at first glance, it seems to do a good job at walking you through the development of an equation rather than just stating it as a definition. So for things like the Riemann curvature tensor, it doesn't just say, here it is. It says, what happens when we take the commutator of covariant derivatives? Having said that, it still boldens the important stuff so that if you need to reference an equation, it's right there. I'm excited to jump into this book because I'm really interested in some of the more advanced topics in GR. So also, since I've been doing the tensor calculus for physics, I was thinking maybe what I could start doing is going over this and then pulling relevant exercises from the actual general relativity textbook. With all of that being said, there's only one last thing left to try. I have a quantum field theory textbook and a introduction to general relativity textbook. Damn it, I thought it would turn into a string theory textbook. Out of these 2 books, quantum field theory, general relativity, which do you think sounds the most interesting to start learning? Let me know in the comment section, and I will see you guys there.